Excellent. Yeah, so my name is Danny Coutts. I'm a new research scientist at the GSC in Calgary, but today I'll be talking about some of my PhD work out on the west coast of Canada, where we were kind of dissecting a really big basin fill. So I'm going to be talking about a lot of the same kind of processes and kind of methods that a lot of people are using for big tectonic research, but kind of maybe a different specific aim. So in tectonic research, time is like one of the really key data sets that we're trying to use because we're trying to understand deformation, sedimentation, cooling, correlation. All these things are going to come up tonight as they did last night as well. And so all types of chronostratigraphic data have uncertainties associated with them. So geochronologic data have kind of these numeric plus or minus uncertainties. Biostratigraphic data are going to be of varying resolution, Paleozoic versus Ordovician versus very specific kind of ages that you can see in the in the geologic timescale to the right. And then we have kind of varying preservation of issues with fossils and ashes and that sort of thing. And so the work that we were doing out on the West Coast was kind of focused on dissecting a really big basin fill, but also kind of looking at how do we integrate all these methods together. So Sam Johnstone at the USGS in 2019 put together a Bayesian framework for kind of finding kind of best fit ages for a single stratigraphic column. So, so on the bottom right here, we have a series of ages, maybe some kind of basement cooling age that would be plus or minus and Gaussian in shape. We have a maximum depositional age, so this would be from a detrital zircon sample. And we know that the age of that deposit has to be younger than the zircon ages within it because those grains had to be crystallized and eroded into the basin before they were kind of cemented together. And then we have maybe some kind of biozone that would have kind of like a square-shaped distribution, then an ash that would be Gaussian and another MDA. And so from these data, we can kind of put some limits on what age any bed can be. And so that's what Sam's work was kind of working on. But regardless, we kind of continually have this issue that a maximum depositional age is effectively anything younger than the grains inside it. So other people have kind of taken Sam's work, like Galen Harrison and McGill has been kind of doing some really interesting basin modeling using this kind of stuff in very old rocks, trying to look at different possibility of sedimentation rates in a basin. And all these kind of Bayesian models work off the same principles. So when we have a stratigraphic column, we know the stratigraphic order of these things. And if we input the distribution of potential ages that they could be from, so again, we have some kind of square-shaped biostratigraphic zone, a Gaussian cooling age, and then these maximum depositional ages, we can draw kind of random values from these distributions. And if they follow the law of superposition, we can kind of log them all in these green posterior distributions. And this kind of gives us these best fit ages that I'll be referring to in green. And so we do that over and over, and you build up kind of a large number of best fit ages. And this kind of allows you to leverage multiple dating methods and integrate them into a single kind of stratigraphic column and start to kind of refine these ages based on other constraints. So out on the west coast of Canada, we're kind of down in the bottom corner. Vancouver would be kind of right under this inset map. And we were looking at the upper Nanaimo group, so a big kind of portion of a Cretaceous age forearc. And the upper Nanaimo group would be in yellow here, where the lower Nanaimo group would be in green. The upper is big turbidite channels. The lower is kind of shallow marine deposits. And the goal of the whole project was to kind of constrain the fill and the age of all these different channel systems and to determine the influence of allogenic and autogenic forces. So if we are able to map out the deposits of these submarine canyons and fans and that sort of stuff, and figure out their age, we can tie them back to what's going on in the Cordillera, be it magmatism, sediment underplating, stuff going out in the Pacific Basin, so changes in subduction vector or subduction erosion, all that kind of stuff. And so this is the work of myself, Rebecca Englert, and Heather Gray, kind of 3 grad student theses that were kind of put together from this. So the Nanaimo group sits atop Wrangellia. So after the insular superterranean had accreted to North America, you had this kind of large forearc area that started kind of filling up with basin. And so the Nanaimo group in yellow here is kind of all that kind of large deposit. There's 3 coarse-grained units in the upper Nanaimo group, the DeCourcy, Jeffrey, and Gabriola. And they're kind of the deposits of these large submarine channel systems. So the coarse-grained units are the coarse-grained channel fill. The fine-grained lithostratigraphic formations are kind of interpreted to be like levees coming off of these channel systems, or the slope of the forearc, as well as the kind of mass wasting deposits in between the channel systems. And then overall, this depositional sequence of these submarine channels is kind of 84 to 62 million years. So when we were out in the islands, we were mapping using traditional field methods, measuring lots of stratigraphic section along the shoreline, because that's where the most exposure is. And we're able to map inland as well, following some of these really kind of high standing ridges that you see in the topography. There's a really strong correlation between the topography of the island and the kind of stratigraphy, where these like very large recessive bays are all fine-grained deposits, and then these really kind of high standing ridges are all very coarse-grained deposits. Large cliffs of conglomerate. If you've ever taken a ferry from Vancouver through Active Pass to Vancouver Island, you'll see a lot of these kind of huge conglomerate cliffs, sea cliffs, just kind of sticking up out of the ocean. So we're able to take all of our field data and create kind of a big basin cross-section, going from the north end of the basin kind of down to the southern end of the basin. On the right of this image, from Hornby and Denman Islands all the way down to Saturna Island in the south. And so we're able to kind of project all of our field data and create a nice image of kind of how these channels would be stacking, and start to kind of tease apart what channels would be kind of together in individual systems. So as far as different types of channels or different types of deposits, we have really conglomeratic channels. So here, kind of demarcated the edge, going from super gravelly conglomeratic fill to sandstone prone fill, kind of at the kind of edge of Saturna Island. So all this kind of orange in this figure would all be conglomeratic dominated channel deposits. We have sandstone prone deposits that are, or sandstone dominated channels that are flanked by levees, which would be this kind of tan yellow. We have these really high aspect ratio channels that are all moving around the seafloor very rapidly, that aren't flanked by levees to kind of house them. And they'd be kind of in this green color. And then we have these large ponded sandstone kind of lobes, the kind of closest thing that we were able to find that would be similar to a submarine fan in this blue color. And so, and then in the fine-grained units, we have these interbedded channel levees, and then more mudstone dominated kind of slope deposits. So we're able to recognize all the key parts of submarine channel systems. And this is kind of the main goals. This is the fill portion of it. So we're able to group like channel deposits together based on their stacking patterns and their fills to figure out kind of the architecture of the ocean basin. But now we need to do the time portion. And so we gathered kind of 37 sandstone samples from the top and bottom of each of these channel deposits, as well as, or channel systems, as well as kind of key stratigraphic markers, dated 300 uranium lead dates at the University of Calgary, calculated the maximum depositional age. And then we were kind of input these into 2 Bayesian stratigraphic models, one for the kind of northern portion of the basin and one for the southern portion of the basin. And we kind of excluded the southern portion of the basin because there's very poor kind of additional constraints. So in this northern stratigraphic succession, you can see that we have some ammonites and magnetostratigraphic data samples kind of intercalated throughout. In the southern portion of the basin, either these biozones are too broad or they occur in places where we can't really use them. So that kind of left us with an issue. So what we decided to do is we decided to calculate our best fit ages from two transects, one in the north, one in the middle, and then compare those best fit ages to the original input ages. And so this kind of allowed us to see how good the original, or how accurate the original data were, the original maximum depositional ages. And so, because if there's an incredible agreement between the original maximum depositional ages and these kind of best fit ages, we might be able to say that the original maximum depositional ages in the southern portion of the basin are okay to use kind of as is. And so when we take all of our, all of these kind of distributions that result from the subtraction of the best fit from the original and add them all up into a very colorful histogram, we can see that the mode of this distribution and the mean as well is very, very close to zero. And so this kind of allows us to say that our maximum depositional ages in this case are representative of the depositional age, and are at least within uncertainty of kind of those original ages. And so if we take that kind of big basin cross section, and instead of in like thickness and distance along the basin margin from north to south, we go distance and time now, we can kind of create some kind of Wheeler-esque diagram to look at when different channels are active at different times. So not only do the channels kind of are kind of clustered into three central fairways, we see that there's a range of channel ages kind of across the entire basin. Periods of non-channel activity when there are active channels in other portions of the basin. And so we're also able to kind of time slice this like a big 3D seismic cube, which is really fun, looking at the different trajectory of different channel systems at different times, which is all great to look at kind of when controlling structures or sediment sources would be kind of turned on. As far as kind of looking at the evolution of the cordillera from the basin, we can see that times of channel sedimentation versus non-channel sedimentation is really hard to kind of reconcile across an entire basin from a single sea level curve. So sea level is probably not a driver. When we look at this kind of really big basin-wide gravel depositional phase, that kind of occurs at the starting of the deformation of the very basement portion of the Coast Mountains batholith of the Coast Mountains. And then this might also be driven partially by changes in subduction plate vector or convergence. And then, so when we go to do tectonic research in general, we have, and we go to use these methods in other kind of aspects of tectonic research. There's a few kind of key takeaways from what we've been able to do by splitting apart this 4-arc basin, is kind of as fine as you can. In general, being able to resolve shorter duration events is always better for tectonic research, because you want to kind of split your basin up as much as possible or have tighter cooling ages and that kind of stuff. And different methods can always help with this, but it's always harder to resolve older events in deep time. So if we just look at a plot of what 1.5% uncertainty in different ages of rocks looks like, we can see that it really starts to curve up. And you might be able to go from measuring kind of less than 1 million year durations when the rocks are really young to maybe being able to break apart basin fill sequences in really old rocks. So, and that's partially where these Bayesian chronostratigraphic methods kind of come in, because you may be able to get better best fit ages, but again, you're going to have kind of big error bars on those. As long as you know kind of the sequence of stratigraphic of like cross-cutting relations, you'll be able to kind of implement these. And it'll be really cool to see kind of where they go from cooling to deformation to veining, mineralization, lots of very interesting basin Cordilleran scale problems that we may be able to get a lot of really information from, especially because we can, once we have great dating data sets, we can start to kind of really talk about rates of various things and time transgressive things that are really interesting. So that's about it. Thank you so much.
Okay, so does anyone have any questions there for Daniel? If you've got any questions, you can, Felix, yes, please.
There's also one in the chat.
Oh, okay.
It's not a question. Great talk, by the way, Daniel. I just wanted to tell the petrochronology community that I just saw a talk at the GSA by Ian Hillenbrand, working with Mike Williams, and he uses a Bayesian approach to reduce the uncertainty of monocyte ages. So I think this approach is seems to be very powerful. Don't you think, Daniel?
Yeah, and it's I think we always have to be careful with kind of how we interpret these things, because and how we kind of gather and put these models together. But yeah, I think that they'll be incredibly powerful for trying to bring all this data together.
You cited Johnston. Would it be the best place to start with this method, or?
Yeah, for like big chronostratigraphic, like for like a stratigraphic section, for sure. I know that there's, if you're an R programmer, like Galen was using bcron, which is an R package for this kind of stuff. It does some Bayesian stuff for, I think, like carbon isotopes, but then he was kind of ripping out the back end of it to do other stuff. Yeah.
All right, thanks.
The question in the chat is about datable bentonites in the Nanaimo group, and that's not in, we don't really have any in the upper Nanaimo group. I think they've been able to grab some out of the lower Nanaimo group where it's a bit more like fluvial, shallow marine dominated. All of them get really reworked in the submarine realm.
Okay, so another question for Daniel from anyone? You can just unmute your mic and give the question.
I have a question, actually.
Yeah,
Great talk. Really enjoyed it. I'm wondering if you can go back to your Wheeler-esque diagram.
Sure. This guy.
Yeah, and yeah, this is I really like the visual and how it's laid out and how it can really show the distribution and in time. I'm wondering, in the central and northern fairways where you do only have well, where it's showing those younger channels from predominantly the maximum depositional ages, have you been able to rule out in this case that that's just not a source sampling issue, where they just potentially didn't sample an older source that the southern fairway was connected to?
Yeah, so when we're all the samples, especially in the, yeah, so all these samples have like a large variety of detroidal zircon ages in them, going from like the time of deposition, which is like 84 to 65 ish or 60 ish, all the way back to like Proterozoic Archean ages. So so yeah, we know that yeah, we know that those samples, like, and we see the progressive, like, yeah, we see the progressive younging. So even before we do this Bayesian approach, like stratigraphically, these all make sense with like some very loose biostratigraphy that we have in the southern portion of the basin. We know that these are like, they're in the right place. We just can't really use this method to assess the accuracy of them specifically.
Okay. Yeah, I think I just totally asked a really dumb question, but I'm getting you now.
Don't worry about it.
Awesome.
Hello to you all. So I'll be talking about oceanic core complexes and which are preserved in the Ophiolite record. So first of all, a quick reminder of what exactly an oceanic core complex is. So here we have a block diagram of an oceanic section with the crust here and the mantle. Oceanic core complexes are actually domiform-like shapes formed on the oceanic floor along slow spreading ridges. So ridges that have a spreading rate of less than 4 centimeters per year. Oceanic core complexes actually allow the mantle to be exhumed near the oceanic surface along detachment faults. Oceanic core complexes are usually related to episodes of low magmatism to amagmatic episodes along the slow spreading ridges.
Thanks.
What exactly are ophiolites? So ophiolites are pieces of oceanic crust that are placed on top of the continental margin during mountain formation and oceanic basin closure. A piece of oceanic floor that has the complete sequence looks something like this, where we have the mantle peridotites, ultramafic cumulates, layered gabbros, isotopic gabbro, sheeted dike, and basalts. But in an oceanic core complex sequence, we have something like this. So basically we have the mantle peridotites in direct contact with basalts, but the lower and the middle crust are mostly missing. Now, ophiolites have been studied for many, many years, and there's different classification schemes for ophiolites, like the HOT versus LOT by Nicholas. Delac has a certain classification, Bakaluva. For the purpose of the study, I'm going to be talking about the Tethys versus the Cordilleran type ophiolites. So this classification scheme applies to the suprasubduction ophiolites. A suprasubduction ophiolite is basically a ophiolite formed on top of a subduction complex. So Tethys type ophiolites are usually complete sections of oceanic crust placed directly on top of a continental margin, and it's usually a passive continental margin. This kind of ophiolites are usually associated with more normal type mid-oceanic ridges formed in oceanic basins. For the Cordilleran type of ophiolites, they're mostly dismembered section of oceanic crust. They're related to subduction complexes and volcaniclastic material. The relationship with the continental margin is usually ambiguous. And their genesis is usually related to back arc basins, fore arc basins, or within arcs. So for the purpose of the study, we wanted to have a closer look at the tectonically accommodated spreading ridges and the oceanic crust formed in those settings. So basically, if you remember, oceanic core complexes formed during slow spreading in tectonically accommodated spreading settings, rather than magmatically accommodated spreading settings. So to study this Tethys and Cordilleran type of ophiolites, we chose 2 case studies. The first one is the Meredita ophiolite, which represents a Tethys type of ophiolite. Here we have a general geological map of Europe on the Mediterranean seashore. So Meredita ophiolite is part of the Dinaro-Hellenic Alpine Fold Belt, which is the result of Mesozoic to Tertiary convergence and the closure of the Tethys Ocean. So if Meredita ophiolite is part of the Hellenic Peninsula right here, so let's have a closer look at this area. So Meredita ophiolite is right here in green. It's part of the Meredita-Pindos zone, which is an ancient oceanic basin. To the east, we have the Corabi-Pelagania zone, the Vardar Oceanic Basin, and to the east is the Adriatic platform, which is a passive margin, on top of which the ophiolites were abducted. So if we have a closer look at the geology of the Meredita ophiolite, so basically the Meredita ophiolite is formed between 160 to 170 MA, and it's abducted also roughly during the same time, so between 162 and 171. So this means that this ophiolite was placed on top of the continental margin shortly after it was formed. So why this ophiolite is interesting? It's because if we look at its geology, we see 2 types of transition between the mantle rocks and the crustal rocks. So basically, we see the eastern type massives that we see here in blue, and the western type massives. In the eastern type massives, the transition between the mantle rocks and the crust, it's a normal petrological moho, where we have the ultramafic cumulates, isotopic gabbros, sheeted dikes, and basalts. So we have the complete sequence. While in the western type massives, we don't have this complete sequence. We basically have the ultramafic rocks in direct contact with upper-crustal basalts. So for this study, we chose to focus on the western type massive. So basically here we have a map showing a more zoomed map of this area here of the Puka massif and the Krabi massif. So for this study, we looked across a section between AB and CD here, where the contact between the mantle rocks and the crust is really well exposed. So if we have a look in this area here, we have a closer look. What do the rocks actually look like? So basically, we're right here. So we have these large zones of reaching up to 100 meter wide of amphibolitized and sheared crustal and mantle rocks that we see right here with the foliation forming. Gabbro injections are quite extensive along the foliation. Locally, they cross-cut this foliation, and these gabbro injections also form large bodies of gabbro injecting the peridotites. So basically, this is what it was interesting to see here. And also, it's important to note that this deformation is entirely ductile. Still along the mantle crust boundary in the western type massives, we see brittle ductile deformation along contacts between mantle peridotites and upper crustal rocks. Here, in this case, it's some microgabbro to gabbro. So we basically see amphibolite schists forming along this contact. And we also see brittle deformation, such as high angle late normal fault offsetting these brittle ductile zones and the amphibolites that I was just presenting before. So basically, this is why we call this boundary between the mantle and the crust in the Meridita Ophiolite the Meridita detachment system. It's because we have actually span of deformation from ductile to brittle, and we see overprinting relationship between the two. Well, between all of brittle to ductile. If we have a look at the microtextures of the rocks that we see along the Meridita detachment system, so basically here we have amphibolitized peridotite, which has been completely amphibolitized. There are some local plagioclase, and we see this melanitic shear bands that develop. Also, some gabbro-derived amphibolites forming along the Meridita detachment system. So we see layering formed by amphiboles and plagioclase, and you also see titanite and zircon. So I'm not going to show any more dating diagrams, or I won't be talking about it for the purpose of this presentation, but just to mention that we did date these rocks, and they actually, the ages we obtained are older than the ages of the metamorphic sol. So that's how we know that these amphibolites are most likely something formed before the ophiolite was emplaced under the continental margin. So here, just a photomicrograph of a tremolite schist. So we see the amphibolite class in a matrix of fibrous tremolite wrapping around this class. So this would be part of that brittle ductile shear zones. And we also have some carbonate breccias with serpentine class. So then we looked at the amphiboles along the Meridita detachment system because they're so extensively present and they're quite easy to work with, well, in a way. So we looked at the temperatures of these amphiboles, and basically we see that titanium content decreases as the temperature decreases. And basically what we see is that we do have some magmatic amphiboles, and they're gradually overprinted and recrystallized to secondary magmatic hornblende and eventually to actinolite tremolite, as we saw in the schist. So basically this is consistent with exhumation along the Meridita detachment system. And obviously, like, I'm not showing here all the textures that we've seen, but we do see overprinting relationship between all these amphiboles. So from this, we build model for oceanic core complex evolution for the Meridita ophiolite. So basically, in Meridita ophiolite oceanic core complex, we do see extensive gabbro injections, and most likely the peridotite-derived amphibolites that we saw are the result of impregnation by this gabbro in the mantle, and that was proposed by Nicholas and collaborators in 2016. So this would be the incipient Meridita detachment system. As the detachment evolves, these high temperature shear zones are brought to the surface, and they are overprinted by brittle ductile deformation. And eventually, as the detachment evolves, we form the last increments of deformation, which are these late high angle normal faults, which overprint the previously mentioned shear zones and shear bands. And then the oceanic core complex, so exhumation along that detachment faults stops, and then magmatism begins again, and we form the eastern type crust. So basically, this is what we have for Meridita ophiolite oceanic core complex. And now, if we have a look at the other type locality, which was the Cordilleran type, we chose to study the ophiolites of the Atlant terrain. Here we have a general geological map of the Canadian Cordillera with Yukon here, BC, Atlant terrain is right here. So let's have a closer look at its geology. So just to mention that the Atlant terrain, so previously to work done by Zagorevsky in 2021, well, before that, the Atlant terrain and the Cache Creek terrain that we see here were basically the Cache Creek terrain, but now they're divided into Atlant terrain and the Cache Creek terrain. So the ophiolites here are part of the Atlant terrain. So we see here in this purple color, we see the volcanic rocks, the basalts in green, some gabbros here. This lighter blue is limestone, and some overlap a sandwich. So also work done by Zagorevsky and collaborators showed that in the southernmost of the Atlant terrain, we have this kind of sequence for the ophiolites. So basically we have the complete sequence with the mantle tectonites, the ultramafic cumulates, gabbro, sheetodike, and basalt. Although this section is dismembered, all the units are there. But in the north, we see this kind of section. So basically mantle tectonites in direct contact with basalt, with very little sheetodikes and gabbro. So that's when the question came, is this geometry that's preserved from the oceanic floor, or is it caused by abduction or later dismembering? So to study this, we chose the Squanga Lake ophiolite, which is one of the northernmost ophiolites in the Atlant terrain here. So we're right here. This is the local geology of the Squanga Lake ophiolite. We have ultramafic rocks with some gabbros, the contact, and some extensive basalts. So here we're looking, so if we're here, we're looking towards south-southeast. So basically, we mapped this area, but we focused on the boundary between the mantle and the upper-crustal rocks right here, which we called the Squanga Lake detachment zone. So basically what we see along this detachment zones are serpentinized peridotites as quite extensive, like as we see here, in direct contact with upper-crustal rocks, such as some granular gabbro as well. And also it's injected by thin deformation dikes. This is a photo of some CS structures in the serpentinite showing a normal motion with the basalt sliding on top of the ultramafic rocks. Here's just some microstructures of the Squanga Lake detachment zone. I think I'm just going to skip this for now, just because I know I have a lot of slides, but we could always come back to it if you have any questions. But anyway, based on the field work that we've done and all the other methods we've used, we interpreted this A-B section. So here's A to B. So basically, here are the mantle peridotites, which are in direct contact with upper-crustal basalt. And the contact between the two is a detachment zone, so the Squanga Lake detachment zone, along which we preserve brecciated gabbro. And we also have some cluster of lower ultramafic cumulates, so lower crustal units. And these are cut by some dikes, which are coeval to the formation of this shear zone. So this is all based on dating that we've done on these units. So that's how I interpreted that this is probably a syn-oceanic structure that is preserved in the Canadian Cordillera. So again, we looked at the thermometry of the amphiboles along the this shear zone. So we wanted to compare with what we see in the Merdita detachment system. So basically here, we also have high temperature amphiboles, overprinted recrystallite to secondary amphiboles, and such as magnesio hornblende and actinolite tremolite. So basically, this is just an image showing that both amphiboles from the Squangal Lake detachment zone and the Merdita detachment system overlap. So just to conclude, what do we take from the Tethyan versus the Cordilleran type oceanic core complexes? So basically, in both cases, we see deformation spanning from ductile to brittle deformation. We see magmatic amphiboles, which formed at quite similar temperatures here. We do see recrystallized secondary amphiboles also formed at similar temperatures in both settings. And one of the main distinctions that we see, it's in the Merdita detachment system, we do have large masses of gabbro, which probably caused the amphibolitization of some of the mantle rocks, which we don't observe this in the Squangal Lake detachment zone or in the Cordilleran oceanic core complex. Is it because we haven't identified it yet? I'm not sure. That's still a question to answer. Thank you.
Okay,
Sorry.
so we haven't got a full time for questions, but has anyone got any questions for Adina?
Yeah, I'm just I had it in the box already.
Oh, sorry, I hadn't been looking at the chat. Yeah, okay, go ahead.
I've mapped serpentinites, and so in Spain, and we well, it was in the 60s, and that was the first ideas. One of my supervisors was Professor de Roever, who started recognizing that these were maybe transported mantle rock that were serpentinized. So is that what you're seeing in the Yukon? I haven't been there, but I guess when you talk about tectonic, what is it? You talked about mantle tectonics. Are those serpentinites, or what kind of rock is it?
Yeah, so I mean, the contact between the mantle and the crust, yeah, they're fully serpentinite, but they're actually pretty pristine preserved peridotites. So yeah, I haven't mentioned that, but in the Squangal Lake, they're mostly Hasburgites, 2 clinopyroxene rich Hasburgites, while in the Merdita, they're mostly, they vary from Yerzolites to Hasburgites. But yeah, there are extensive serpentinites at the contact between the mantle and the crust because they're close to the surface.
Yeah. Oh, that's nice. If you have really peridotites there, clearly.
Yeah. Oh, definitely. Yeah, they're real mantle peridotites, tectonites, and yeah.
Good.
Okay, has anyone else a question? I'll just wonder then, Dina, just how common are these core complexes? And do you think that there are other areas, whether it's in the Alpine chain or Cordillera or elsewhere, that may have been misinterpreted in the past?
Yeah, I mean, probably. And I mean, in the Canadian Cordillera, as we saw in the Atlan terrain, most of the northernmost Ophiolites, they don't have the complete sequence. So there's definitely potential for oceanic core complexes. And also in the Alpine, yeah, there's many studies that show that there are oceanic core complexes preserved. And now they're actually even looking the Arabo-Nubian shield for oceanic core complexes, and actually because they are interesting structures, because they could be associated with mafic, ultramafic VMS style deposits that have been a little bit maybe misinterpreted or overlooked, because we don't look really for VMS deposits in ultramafic rocks or mafic rocks like these, or this kind of settings. So they're definitely very interesting structures to look at. Because in the Mirdita ophiolite, there's a series of VMS deposits following the parallel to the detachment, basically.
Okay, thanks very much. That's very interesting.
So, this talk is derived from a paper published earlier this year in EPSL. What we wanted to do in that paper was to bring some hard geological data on the vigorous debate about Mesoproterozoic tectonics. Because I don't know if you've seen, but there have been many papers about debating about where was there any plate tectonics occurring in Mesoproterozoic, and but most of these debate revolve around proxies, like the composition of the chemical composition of zircon in a global database of detrital zircon, or the isotopic strontium composition of ancient limestone, things like that. So when I was looking at the proxies and the tectonics that could be implied, I wonder if we could apply the tectonic model that is accepted generally for the Grenville Province. So I just wanted to go back. When I started to study the Grenville orogen, it was in 2011, and Toby Rivers had just published that amazing story proposing that the Grenville orogen was similar to what we consider as a large, hot, long duration orogen, similar to the Himalayas, with periods of channel flow, especially in the first part of the Grenvillian orogeny between 1090 and 1050 MA, which is called the Ottawan phase of the Grenvillian orogeny. And then he proposed that this thickening phase involve long period of ductile flow of a partially molten crust, and then it would have convergence would have been reduced or stopped. The orogen would have collapsed on itself, forming metamorphic core complexes, and then for some reason convergence would have renewed and propagating the orogenic front toward the foreland, generating what he called a small core cold short duration orogen that would have reworked the Laurentian basin. So I was really excited by all this because I had been studying this for my doctoral and postdoctoral study, and I had been building field tests to determine which model. Which of these models allow.
Excuse me, Felix, just to interrupt you, but you're breaking up a lot. Is there any loose connection, or is there anything that you can do to get a better voice?
Is it better now?
Much better, thank you. Sorry to cut you off, but if you can go ahead now, it's great.
Okay, sorry about that. I have to change computer, I think. All right. So, as I said, I was excited to see all these models because I had been testing them in my doctoral and postdoctoral studies. And if you look at these diagrams, a structure comes up often is the ABT, which is the abbreviation for Allochthon Boundary Thrust. That would have been the thrust fault of a channel in the Ottawan. Then that would have been reworked during the collapse of the orogen. It's called the ABD here. And then it would have behaved as the roof thrust of the small coal orogen during the Rigolet phase, the last phase of the Grenvillian orogeny. So I decided to go in the field and put my students in location that you see with the rectangles in here to study that boundary. And what we found was very different than what the model suggested should have been. This is a compilation of the northeastern part of the Manicouagan Reservoir. All the dates that you see there most of them are dates that we have obtained on both sides. Some are from the literature, but all of them are dating deformation, high temperature deformation, or metamorphism. And all the dates that you see here are regolith. So whether you're in the alloctonous belt or in the paratoctonous belt, everything is regolith. So the regolith, a younger phase, was long, hot. It involved pervasive partial melting of the Archean basement that flowed ductilely for a long period of time. So you see some example of magnetites. In the alloctonous belt, the melt rose in the upper part, that was in the upper plate, which was the alloctonous belt, and it dismembered it and carried it as block that you can see here as amphibolite into the flowing channel. We've documented that in the northeast part of the Manicouagan Reservoir and along Highway 117. We can look at Chris Lambert's research. Same thing, protracted melt present deformation in the regolith. But then the question started to build in my head. What kind of tectonism could do that? You had an origin that collapsed on itself after a collision phase with another continent, and then you have a renewed convergence strong enough to build a very hot origin that allowed an Archean dry basement to be partially molten and flow. I had a hard time understanding that. So let's look at the collision to better understand. What's the best estimate of the collision itself? Well, Marsh and Kulsha dated several eclogite layers, and they dated zircon with typical high pressure profile, and it yielded ages of 1095. What was going on in Laurentia at 1095? Well, the entire continent was under extension. In the Arctic, you had major rift basin that were developing. And closer to the orogenic front, you had major rift in the southwest large igneous province developing, producing large volume of mantle melt and placed in the rift. So this is really weird. You had a major collision between two continents, but yet you put the continent under extension. And this was the main argument of Bob Stern. That was one of the arguments of Bob Stern to suggest his Mesoproterozoic single leak tectonics model, because he said that doesn't make sense. Furthermore, in the mid-continental rift, the sediments have texture indicating it had access to the sea. It's marine texture. You have wave changing, you have chicken wire texture, and the chemical composition of the sediment indicates that it had a marine origin. So you're behind an origin and you had marine sediments. That's strange also. Another inconsistency comes from the paleogeography study by Swenson Isel et al., who dated several layers of volcanics in that mid-continental rift, and he reconstructed the paleogeography of Laurentia from these layers. And he determined that Laurentia was moving south at a blistering pace in excess of 20 centimeters a year between 1110 and 1080 MA, which is the exact same period that you had the presumed collision. So this doesn't fit with an upper plate setting for a continent, and it doesn't fit either for a continent undergoing collision. So then, if the model suggests that Laurentia was a continental arc for a protracted period in the Mesoproterozoic. So all the data that we presented up to now suggests that it was the lower plate instead. But how did it get there? So we have to examine the continental arc formation period to see if it holds with the fact. So here's a compilation map of all the Archean or pre-1.8 GA rocks in the Grenville Province, along with younger than 1.7 GA granitoids intruded in the paratoctonous belt. you see that these granitoids only occur in the southwest Grenville Province. The remaining of Archean and older of pre-1.8 G rocks are in the Tectonics Group. Now, that I find strange because it was supposedly a continental arc built on Laurentia. How come there's absolutely no igneous rocks in the basement? It should be there. Then, if we look at the archetypal continental arc origin, the Andes, all the dates that you see in here are basement that crops out at the surface. Remember that the Andes is a young origin. The erosion level is low compared to the Grenville. But in the Grenville here, remember that these are all the rocks in the entire Grenville province that are 1.8 and older. There is absolutely no basement rocks cropping out in the alloptonous belt southeast of the allopton boundary thrust. If we look at the chemical of the geochemistry, on the Pierce diagram, the mafic rocks in the Andes plot are enriched in thorium, as they should if they're contaminated by the crust. In contrast, the Grenville rocks plot in the subduction field here or along the Montelare. More convincingly, this is a diagram compiling the difference between the neodymium model age and the emplacement uranium-lead zircon age for all the points for which we know both the neodymium model age and the uranium-lead age. You can see that in the Andes, there's a large spread, there's a large difference in ages because the young igneous rocks are contaminated by the old basement. In the Grenville, the difference is theoretically larger between the basement and the igneous rocks, yet the difference is within the error of the methods. So that doesn't fit with the continental arc neither. Then last year, and for many years, the leaders in petrology of A-type granite, frost and frost, have argued that the A-type granite that crops out in the US as the granite rhyolite province that have been correlated with the alloptonous belt in the Grenville province could not be formed in a back arc or any arc setting. Yet the model involved a continental arc across the entire Laurentia. So that's another inconsistency. So what do we do if the current tectonic paradigm for the Grenville doesn't work? Do we have to go back to Bob Stern and say that the Mesoproterozoic, there was no plate tectonics? I don't think so. I think there's a way to resolve that. But we have to remove Laurentia from the equation. Let's say that for most of the Mesoproterozoic, you had oceanic arc building in an ocean very far away from Laurentia. And then that these arcs collided together, and perhaps with another continent such as Amazonia, at around 1150 during the Shawinigan orogeny. Then if this oceanic plate was accumulating at the mantle transition zone here, its weight would have built. And then suddenly at 1009, what is called the Ottawan phase of the orogeny, if the slab suddenly pierced the mantle transition zone, then you would pull rapidly on the oceanic plate attached to Laurentia, putting Laurentia under extension, forming the mid-continental rift and the Arctic basins, and moving Laurentia very rapidly toward the south, toward that continent which we term Shawinigan. And this could have produced a continental arc with some deformation, and I suggest that this is the Ottawan phase of the orogeny. It would have been a continental arc. Then the collision would have occurred much later at 1030 approximately, and producing the Regal phase of the Grenvillian orogeny, which would be actually the Grenvillian orogeny, explaining why we document such widespread melting of Archean basement. And then the slab would have broke off. This model is supported by geochemistry for rocks emplaced during the Grenvillian orogeny. So these are the felsic rocks. You can clearly see that there is a trend from arc to A-type granite between 1150 to 1030 MA. Similarly, with the mafic rocks, pre-Ottawa and mafic rocks taught in the subduction field, as they should. Then, as you develop the Shawiniga continent, you then form a continental arc, these green spot here. And then as the collision proceeds, the slab broke, and then you go back to the mantle area. So there's a support from the geochemistry for this model. So I would like to thank all my student warrior and my collaborator for this study. Thank you very much.
Okay, now thanks, Felix. So has anyone got any questions for Felix? Surely there are some questions on a rather controversial topic. Well, maybe I'll just start off then in asking about the mid-continent rift. So getting away from the Grenville, are you saying that the traditional models for mantle plume origin, or more than one mantle plume origin for the mid-continent rift, are not correct, and that's just part of a general period of crustal extension?
Well, extension fits with the extension we see, but there could have been a plume as well. I don't have a problem with that.
Okay.
I don't see why there wouldn't be a plume.
Yeah, thanks. So anyone else working in the Grenville have a comment or especially a question for Felix, please?
Felix, I've got a quick question.
Yes, so go ahead.
Yes.
Talk. Yeah, really cool talk. I've got one question. Why would the slab avalanching cause compression in the upper plate above it?
Aha, you found the weakness of the model.
Okay.
Yes, well, that's a very good question. Probably because of the fast rate of subduction, I would say. There is one study, one numerical model of slab avalanche, and it resulted in compression in the upper plate. So this is basically the only argument I have to put forward for this. I think it's worth future study.
Cool. Weird and interesting. Thanks.
Yeah, I was gonna ask the same thing. Like, I agree with you that the Rigolet may be a lot hotter and more liquid than we usually see it. But if you step away from the ABT, then during the other one, there was also a major metamorphic event on a much wider zone than the paratectonus belt. So yeah, same question as Tyron. I'm wondering how you create that with only the slab avalanche. So
well, there may be
anyway,
other things. Yeah. We're supposed to be in the transition zone between the Archean and the Phanerozoic. So there could have been a lot of things going on. I don't know, delamination, mafic ponding at the base of the crust, or there could have been a lot of things producing the metamorphism that we see. But we do need a compression driving force, that's for sure.
Yeah. So what would be the smoking gun to prove or disprove your model? Ophiolite and the ABT?
Yeah, that would be it, I think. But we're so deep. But there are a lot of mafic rocks and ultramafic rocks along the ABT. So we should ask Adina what would be the key feature to look for.
So Dennis, you had a question, and then there was Dan, just to finish. Oh, and Bruno.
That's quite an ambitious project there, Felix. Thank you for the talk. I've got sort of a navel gazing question. It always surprises me that people seem to be surprised that the Grenville looks different at different parts of its 1,500 kilometer long or whatever it is exposure. Isn't it a little bit like the blind men studying the elephant? we're all seeing details of parts, and your challenge is to put them all together into something that is a homogeneous mess, meeting another homogeneous mess in a way that we don't really understand.
Is that a question or?
Yeah, I'm asking if it, like, is there an element here? You talk about the difference between the one end of it and the other, and there's things here and things there. How much of that is the difference in mapping or knowledge of the belt itself, and should we expect it to be the same everywhere we look at it?
That's a good question. That's exactly what we try to do in that paper, to look at the big scale. So the geochemical data that I've presented comes from the entire origin. The Rigolet data comes from at least 3 different transects. So and then I've tried to look at the bigger scale picture. So exactly for that reason, to get rid of I have an outcrop that contradicts your model. So that's what we've tried to do, and that's why I paired with Kyle Larson and Carl Guillemette to have fresh eyes that would be away from the Grenville.
We're going into the break, but as this is, there's a lot of interest. Dan, have you got a quick question, please? Next.
Nice talk, Felix. Not so much a question as a comment. As far as that comment earlier about the upper plate going into compression above that slab avalanche, you also have to consider what motion that upper plate was undergoing. You know, if it's moving toward that subduction system and basically pushing against it, then it's going to put itself into compression. So that's another thing that maybe, I don't know, was it Schwerdtner? Which one was the upper plate at that time?
Yeah, I call it Schwerdtner.
So knowing what its absolute motion was would be interesting, but probably not, something you could resolve. But if that's moving, orthogonally towards the trench at a high pace, then it could be putting that upper plate into compression because of that.
Mm-hmm. Good point. Thanks.
Okay. First, I'd like to apologize because I'm very hard of hearing these days, and I'm likely to speak far too loud. So you can always turn down your volume. Second, I'd like to mention that I was very pleased to see this talk yesterday, the last talk about industrial hydrofracturing in northeastern British Columbia, in the subsurface, in sedimentary rock subsurface, by Taka Karnaya. And he gave a very nice talk about also experiments about industrial hydrofracturing, man-made hydrofracturing. So in the shallow subsurface and or upper crust. And today I'd like to propose that we have examples of deep crustal or mid-crustal hydrofracturing, actually fossil hydrofractures in form of veins, of irregular veins in the Grenville Province. And I'm following the ideas that have been summarized by Bonds and others in 2022 on this subject. So the emphasis here is on an irregular or chaotic veining. And you have 2 examples here. This is quartz feldspar veins or other feldspathic veins here. And here we have biotite veins. This is in the Grenville Province tectonic zone. This is a bit higher up away from the Grenville Province tectonic zone, but not too far. So first I have to put some background information here about these fossil hydrofractures, so-called veins, irregular veins. Okay, so this is from a review paper by Barnes et al., which I recommend to you. It's a very detailed and complicated paper, but it summarizes all our knowledge of what we think about fossil hydrofractures in deep crust or mid-crust rocks. And so the simulated hydrofractures filled with fluids are shown in blue, and the fractured rock is shown in red. If you want to hear or you want to see the details of this review paper, which goes into this modeling in great detail, you have to go to Barnes et al. Yourself. Okay, so I have to tell you a little bit about the conditions, the stress conditions for hydrofracturing. This is more circle. The only one I want to bring here. This is first of all, I usually ask my students, how do you represent hydrostatic pressure or isotropic stress in the Mohr circle? Well, the answer is you put a dot on the abscissa. So as soon as you have shear stress, it's hydrostatic stress with zero shear stress. And so here you have then circles, and the larger the circles, the more shear stress there is. How do you make hydrofractures in natural settings in deep crust? Well, we have to use the Mohr-Coulomb envelope here for failure, for faulting or fracturing in rocks. And we start out with we have to explain the principle of effective stress. Effective stress is basically the difference between applied stress or regional stress and the pore pressure or the pressure in rocks that are highly fractured and therefore have fluid pressure in them. So the more the fluid pressure, of course, acts as if it was a tension applied to the rock. So it acts outward, and it counteracts the applied stress, which is compressive, and in this diagram shown as positive values. So anyway, here we have the starting condition, the red circle, and then we get less and less shear stress because the hydrostatic stress in pressure in the rock counteracting the applied stress is getting more and more profound. And then when because we are subtracting the pore pressure or the isotropic fluid pressure from the applied stress, we get smaller and smaller circles. And as I said, anyway, we don't have to go into all the details here. Anyway, you can see failure here. So we're making, when you have a dot, of course, you have an infinite number of tension directions. Isotropic stress is like a sphere, represented by a sphere. So the stress ellipsoid becomes a sphere, and then you have an infinite number of directions of extension, and you can make many different directions of fractures. That's quite different from regular triaxial stress conditions. Okay. We are in the Ottawa River gneiss complex, which is formerly used to be called Central Gneiss Belt, but Toby Rivers and I proposed that we could rename this thing. And there's other complexes. There's one gneiss complex in the high Adirondacks, and the other further in central and northern Quebec. Anyway, we are obviously in the Georgian Bay region here. Sudbury would be around here somewhere. So that's where we are. Here's some examples of interpreted fossil hydrofractures filled now with veins, and mostly in amphibolites. So it's a lot of text here. You may want to read this as well if you don't understand what I'm talking about. But anyway, the field photo shows a hornblende gneiss with an uneven network of irregular leucocratic veins, initiated apparently by mid to upper-crustal hydrofracturing. And it's local, okay? Because other rocks, which are more felsic, don't have these features. Okay. So the yellow sun hat here on top here is the scale, so you can see what the scale is for this outlook. Okay, where are we here? We'll be talking about the Grenville Front tectonic zone east of Sudbury or southeast of Sudbury. Here's Lake Nipissing. Georgian Bay is just showing here a little bit, Lake Huron. So we are in the interior part of the Grenville. Here's the Sudbury Basin, of course. We will also talk about the Wanapatei igneous complex or meta-igneous complex, which is this little oval here. Okay, so in the following slides, this will come up. Here's photographs of the Wanapatei meta-igneous complex. This is a fairly well-preserved mafic gabbro, I guess. And here's a very nice anorthositic gabbro kind of. You can see the mafic clots have been strained quite a bit. This is the vertical surface. So you can see this is deformed. We are in the hanging wall of the Grenville Front. We're in the Grenville proper. Okay. Not too far from the hanging wall of this meta-igneous complex is this fantastic outcrop here, which is a road cut on a highway east of Sudbury. And you can see here that we have fractures that are filled with biotite. So we have coats of biotite, which are shiny here, and you see they have various orientations. They look fairly haphazard. So this could be called chaotic fracturing, and these are, of course, fossils of former fluid pockets in hydrofractures. Here's the interesting situation. We see that the mafic rocks, especially the amphibolites, have these regular fractures, which are interpreted as fossil hydrofractures. And here in the banded granite gneiss, we have none. We have ordinary concordant foliation parallel veins, but no evidence of hydrofracturing here. So this suggests, of course, that maybe this occurred, this hydrofracturing and this fracturing in general occurred while the Grenville rocks underwent regional deformation. Okay, so I have a few summaries here, and then this is only a pioneering. This is only the first progress report of this project. We started only last year. So the first conclusion: 3D arrays of non-fibrous chaotic veins occur in several parts of the western Ottawa River gneiss complex, and especially common in the Grenville Front tectonic zone and the overlying paratochthonous rocks of the Sudbury North Bay region. Second conclusion: in major high strain zones, deformed units of banded gneiss and disrupted amphibolite layers exhibit interconnected irregular veins of biotite, quartz, or quartz feldspar, apparently initiated by mid to upper crustal hydrofracturing. That's, of course, an interpretation. But if you want to see some more detailed arguments for this, you should perhaps consult the review paper by Bonds et al., 2022. Third conclusion: elsewhere, the hydrofracturing and chaotic veining are restricted to the deformed mafic layers, suggesting that they ruptured while the hosting felsic gneisses underwent solid-state ductile flow. I've already made that point. So, fourth conclusion: east of Sudbury, the hanging wall of the Wanapatei igneous complex includes a body of highly deformed potassic pegmatite, replete with ostensibly chaotic, thin biotite veins ranging in length from a few centimeters to 1 meter. However, the largest biotite flakes cover arcuate fracture surfaces outlining mesoscopic lozenges akin to triaxial foliation boudins. Therefore, the other large biotite flakes mark bent cleavage surfaces in variously oriented, very large feldspar crystals in the deformed pegmatite. So we reckon that the hydrofracturing occurred, during deformation. And of course, we don't have the age of this deformation. The Grenville Front tectonic zone rocks have a long history of deformation. Only the last part of it is related to the Grenvillian orogeny. So this has to be sorted out by dating, by suitable dating of the biotites and others. fifth conclusion, the sum of our field observation points to lithologically controlled and tectonically aided hydrofracturing and migration of metamorphic fluids, possibly at different times during the Grenvillian orogeny. And I'd like to thank again Don Roussel for showing us the Grenville tectonic zone, and especially the Monopotai igneous complex. And this is Toby Rivers, Don Roussel, and myself. And this is taken in a former open pit of this Monopotai igneous complex southeast of Sudbury. Thank you very much.
That was great. Thank you, Fried. Does anyone have any questions?
I will ask one. So Fried, did you notice a relationship between the geometry of those fractures and the rock fabric? Are they always completely random, or can they follow foliation or something else?
Well, the one outcrop with the biotite filled fractures, the largest fractures outline kind of lozenge type structures. So we have not measured the 200 of those fractures systematically and done statistics on it, but we judge them to be, this is only a 1-year-old project, but we think that they're fairly random, but I think that the largest fractures seem to be controlled by Boudin-like structures. And so I think that the chance of, let's say, extension going hand in hand with the hydrofracturing is quite good. But we need to do a statistical study of that outcrop, measuring maybe 200 or 300 vein-filled fractures.
Okay, cool. Thank you.
Felix?
You mentioned fluids, but it looks like granites that fracture your amphibolites. Do you see the same? Do you see them as the same thing, or?
Did you finish your question? Okay. According to our field observations, these are pristine metamorphic veins. They're not intrusive granite veins. So they look like sugary textured, sometimes mostly feldspar, so mostly plagioclase veins. And we interpret them as metamorphic features, not as igneous features.
Okay, it's intriguing. I think it's worth pursuing because I've seen these kind of textures everywhere in the Grenville, in the Canadian Cordillera, in the Himalayas, and I always assume it was leucogranite fracturing the amphibolite.
Can I just go back a few slides here? Just maybe go to slide number 5.
Yeah, if you just share your screen, yeah, perfect.
Hold on. We have here. Yeah, the previous one. One more back. One more. Yeah. So these are. If we go back one more. No, we overshot it. Yeah. Here you see the felsic rocks. This is an ordinary granite diorite gneiss. With foliation parallel veins. And we wouldn't assume hydrofracturing here, but this irregular stuff, and here, this part here, you can see foliation boudinage here. Obviously, this, you can see the necking here. So this part here doesn't seem to have undergone, so the fluids seem to have been very localized, but this is so irregular that we embrace the idea of chaotic veining and therefore hydrofracturing. Fossilized hydrofracturing.
And then what's the white material come from? How it forms?
This is mostly plagioclase aggregates. This is amphibolites, so it's very little quartz in this rock. So it's very, I don't think there's much quartz in here. It's mostly feldspathic veins.
Okay, so it's melting the amphibolite or it's exogenous?
Well, the fluids travel through this rock, and obviously they had pathways like fracture pathways that allowed the migration of the fluids under high pressure. That's our interpretation, and obviously very heterogeneous. See, here we have actually ordinary extensional strain, you know. Here we have the foliation Coutinage. It's just here. So these are local fluid pathways through the rocks, probably in the upward direction. That's our interpretation at this point.
Okay.
Okay, so I don't want to give anybody whiplash from the change of scale, but I'm a geophysics faculty member at Memorial University in Newfoundland, where it is getting quite late. And I thought I would take this opportunity to talk to this group, because I don't typically talk to mostly structural geologists about some of the work I've been doing in Atlantic Canada. Let's see this work. So the motivation behind this, it picks up on some of the themes that were brought up yesterday to a large extent, which was the idea of inheritance. And I spent a lot of time worrying about the role of orogenic inheritance on subsequent rifting and passive margin formation, because I'm mostly looking at the rifted margins of the North Atlantic, specifically those in Newfoundland, Ireland, Iberia, and Morocco, and Nova Scotia to some extent. And on this map, you can see the traces of certainly the zones of Appalachian and Caledonian influence, as well as the Variscan down here. And you can see some peculiar things that happen offshore. We have these continental ribbons like the Flemish Cap and the Porcupine Bank, and these things are not acting like other rifted margins, and it's thought that these are being driven largely by these inherited structures from orogenesis. So the second thing that motivates this is a desire to reconstruct present-day structures that we see now back through geological time, specifically using deformable plate tectonic reconstructions. And as a teaser, this is a reconstruction from my past PhD student, Michael King, which should run now, where this is actually going forward in time from 200 million years to 80 million years or so, just showing the opening of the North Atlantic and the deformation of the continental margins. Now, these are based on crustal thicknesses from today, which are reconstructed back in time, and now we're just playing them forward. But being able to look at the crustal structure in the past, it's helpful to have today, and then we can move it back. So that's the second motivation here. And so for this particular study, I'm focusing on Atlantic Canada. So this is the polygon looking in here. And basically, I want to be looking at crustal structure across this entire region. And you can see there are a bunch of black lines in here. These are all from wide-angle refraction seismic surveys. And then there's this yellow outline, which is from an earthquake study that was done by Fiona Derbyshire at UQAM, trying to get crustal thicknesses from earthquake data. I won't focus on that one so much. I'm going to focus more on these black lines here. And so those are from reflection. So some of these are onshore, most of them are offshore. So in case you're not aware, this is a kind of survey where we want to get velocity structure. So we want to send energy traveling laterally through the crust as much as possible. In the marine case, we actually put an ocean bottom seismometer on the seabed, and then we set off our air guns at increasing distances up to 200 kilometers or so. And we want to be sending energy down through the crust, traveling laterally so we can figure out the velocities. And we also want to get bounces so that we can figure out where the moho is. On land, it's a little bit easier, although the permitting can be a little bit difficult because this involves dynamite. But we put receivers along the surface, we set off some explosions, and we want to send energy laterally so we can get the velocities, and we want to bounce stuff, which is the green bits, to give us the moho depth constraints. So this is worldwide. The best way to figure out how thick your crust is to use these kinds of surveys. And so this is a compilation of the available depth to moho constraints from these refraction lines, which are shown here as little circles. And then this is the average depth to moho from Fiona Derbyshire's work, or her grad student's work, from an earthquake seismic array. And overall, you can see there's a lot of gaps. We have some decent constraints, but there's lots and lots of gaps. And if we know where the moho's at, and we know where the basement's at, we can figure out crustal thickness. And so this is an estimate of crustal thickness based on these ones. Again, great, fantastic, but lots and lots of gaps. So a lot of the work that I do, I am primarily a seismologist, so I like doing, this is actually my line. but I also want to be able to fill in the gaps so that we can do these plate reconstructions. So to that end, what I like to use is gravity, because gravity is everywhere. So this is the gravity coverage across Atlantic Canada. This is the free air gravity data. And what I ultimately want to be able to do is use this, constrained by the seismic results, to get me crustal thicknesses everywhere. So for gravity, I'm going to specifically use inversion. So for those of you who are not familiar with inversion, the forward problem that we can do with any kind of information is build an Earth model. So in this case, a density model, and then we can predict what the gravity anomalies are for that specific Earth model. And this is a linear problem. This is not a problem. We know the physics. And then inversion problems are kind of magic in some ways, because what we want to do is get the Earth model directly from the gravity that we observed. Now, this is magic in some ways, because there's a lot of non-uniqueness involved with gravity, and so there's a lot of Earth models that can satisfy those observations. So the only way to really make this doable is to to use constraints. And then we can find a model, hopefully, that satisfies our observations and also satisfies our constraints, whatever those happen to be. So traditionally, the way that I have done this, mostly in the offshore, has been using a constrained 3D gravity inversion. And this is an example shown for mostly offshore Ireland, but you can see the island of Ireland here. And effectively, to do these models, we build an initial model where we use bathymetric constraints, which are available everywhere, and depth to basement constraints, which are available everywhere of variable quality. Now we build an initial model with this. We tell the inversion algorithm that water is water, and sediments have to follow a specific relationship of depth as a function of density as a function of depth. And then we take our satellite gravity observations, which are available everywhere. So this is an example for Ireland. For the sediments, what we do is we use these density as a function of depth relationships to tell the model, for instance, that densities have to start here, let's say, and have to vary as a function of depth when we get the inverted model. And then if everything works, I happen to use an algorithm called Grav3D, which was developed at the University of British Columbia. And if everything works, not only do we get a predicted data set, but we also get an inverted 3D density model, which we can slice and dice any way we want. And we can also pick an isodensity surface, and let's call that the MOHO. And now we have a map of the MOHO over this area. Since we already know the depth of basement, we can calculate crustal thicknesses. And further still, we can subdivide that crust into different layers and try and analyze those. And so this is effectively what I want to be doing for Atlantic Canada. And so these are the gravity data that I showed you before. These are our observations. The depth to basement had to be a bit cobbled together. This area 1 is from the Geological Survey of Canada. Area 2 is actually from the Crust 1.0 model, which has issues which we can chat about if people want. And area 3 is from a global compilation of sediment thicknesses, which we then just subtract from the bathymetry to figure out where the basement's at. So those are our inputs that go in there. Things get a wee bit tricky, though, when you're trying to come up with a model that can deal with thin oceanic crust, thicker continental crust, and onshore topography. And so this latest paper, which actually was accepted for publication just yesterday, I came up with a new way to deal with these data. So I showed you before, these are the trends that we have for different lithologies for density as a function of depth. The way the inversion has been set up in the past is that I would just have a starting density shown by these black lines here, and then the densities are allowed to range over these gray boxes down to the depth to basement, and that would characterize my sedimentary column. The tricky part, though, is that if you look at this plot here, which is showing you density as a function of depth for instance, continental crust, which is shown here by this black line, and this is from the Christensen and Mooney paper, versus oceanic crust, which is a great deal faster, you can see it's really hard to come up with a model that's going to distribute the densities in the same way that will be able to capture oceanic versus continental crust. And as it turns out, the approach that I wound up using was just to spread those densities over a different depth extent, and spread them over a greater depth extent for continental crust and over less of a depth extent for oceanic crust. And so to design that, I basically am using a bit of a fudge, but in the absence of other constraints, this is the best we can do. So I take the bathymetry and topography for Atlantic Canada. I do a 50-kilometer upper continuation, which is basically a smoothing. And then I design the base of my inversion mesh a bit like an iceberg. If you think this is the top of the iceberg and most of it is underwater, this is basically showing that for these deeper parts, I'm going to spread my densities over a greater distance range. And under the oceans, it's going to be forced to be more compact. And then I build a reference model like this, and you can see it's got this variable mesh depth at the bottom. And this is one view, and then we spin it around and you can see how it looks differently. This seems to work quite well. And ultimately, these are the data that are predicted from that model, which if you don't recall what the observations look like, if we take the difference, this is what the difference looks like. So the model that I get out of this is actually very good at reproducing the observations, which is nice. And then we can actually start looking at the model itself. So this is the model, and you can see this is the variable mesh depth down here. Now I've got a range of densities here, and I have prescribed a MOHO proxy as corresponding to a specific isosurface in the density anomaly model shown here. And if we take this, we can then compare it with what we get from the refraction seismic data. And in fact, what I'm showing you here is now I'm showing you the depth to basement, and then I've taken away the parts that are corresponding to the mantle, and this is just the thickness of the crust. And then this is what it is plotted as a map. On top of this map, I have included the little dots here from the refraction survey. So you can see how well the crustal thicknesses from the gravity inversion match with the crustal thicknesses from the completely independent seismic constraints. And where they tend to disappear, it means the match is super, super good. Places up here, the match isn't so good. This one is explained by there's a massive underplate, which the inversion will interpret as mantle. So that makes sense that this doesn't match. But places here, you can see the match is actually quite good. And you can't really see the refraction constraints because they're blending into the results from the inversion. So that gives us some confidence that this is not bad. Now, the other thing that we can do, since we have a crustal thickness, we can then split this crust into an upper crust, a middle crust, and a lower crust based on some arbitrary density divisions, and then take those different crustal layers and plot them as a percentage of the overall crustal thickness. And that's what's shown here. So this is the percent of the full crust that has higher densities, which we would associate with upper crustal rocks. And so you see the higher percentages occur where we know we have continental crust. So that's kind of encouraging. And we see in the oceanic crust out here, we see low values, which makes sense because we shouldn't be having high or low densities associated with more felsic crust in the oceanic domain. So this is an interpretive tool. It can help us to figure out where the edge of continental crust may or may not be. So that's quite nice. We can do the same thing for middle crustal densities. And here, when you do that, you see there's this interesting area here outboard of Nova Scotia and just south of the Grand Banks that has really, really low mid-crustal densities. It also didn't have upper crustal densities. So that means that this whole area here is incredibly high density, or the crust is completely gone away. So this is another way to look for exhumed mantle, a little bit like was discussed in a previous talk. So you can have these large zones. And then finally, if you look at the percentage of the lower crust, this thing lights up like a Christmas tree in the offshore domain where you have oceanic crust, as it should, because that should be much higher densities associated with lower crustal rocks. So these are ways that we can take this 3D model and exploit it and help us characterize the crust in different places. The other thing that we can do is we can slice and dice this model any way we want because it's a 3D cube. And so this is an example here where there is a refraction line here called SMART1. This is the velocity model that came from that. And so we could not only slice our model to correspond to the same areal extent as this model and overlay them so that we can see how well these boundaries that are constrained mostly by reflections, we can see how well those match our model, but we can also go further outboard. So this one is actually going all the way from the Maritime Basin over here, all the way across the shelf, and then all the way, way out into oceanic lithosphere beyond where that seismic line extended to. And you can see this one crosses the Orpheus Graben right here. You can do that for other lines as well. This is one that goes across the island of Newfoundland. In fact, it starts in the Strait of Belle Isle over here, goes across the island of Newfoundland, goes across the Grand Banks, and then goes across the continental shelf over here, crosses over where we have this Screech 3 line here, which is the velocity model is shown here. And then again, we could take these boundaries, overlay them on top of our densities and see how well they match up. And we see some interesting things on this one in particular, because you can see the MOHO from the refraction has this really big step function, Whereas as far as the densities are concerned, it doesn't see such a big jump, which may imply that we have higher density lower crust here than is inferred just from the velocities alone. So there may be some intrusions or whatever. That's another debate. You can also see here, we got low velocity mantle here, which is assumed to be serpentinized mantle. And you can't really tell it from the gravity, which makes sense because the densities are going to look very much like lower crustal rocks or serpentinized mantle. So it's really hard to get that boundary from density alone. And then this is the last line. This is going basically from the tip of Cape Breton all the way across the island of Newfoundland, all the way across the Bonavista platform, across the Orphan Basin to the Orphan Knoll, all the way out. This is a refraction line here, corresponding down here. Again, same thing. And this is an interesting one where there is a wee bit of a mismatch in terms of where the gravity inversion tells you the MOHO should be and where it actually is. This is interpreted as a failed rift, and the inversion doesn't really see it. And that's a consequence of using the bathymetry to figure out where the depth of our mesh should go. In this case, we have really, really, really thick sediments. And so the inversion can't possibly know that. In truth, what it should be doing is bringing the mesh up higher, which would push the MOHO up higher and give a better match. But we only know that because of the refraction. And in the absence of that, that's one of the limitations of this method. And then ultimately, we can take the crustal thickness map and we can overlay it with whatever we want. Here we've got Appalachian deformation front and a lot of the sutures and boundaries from the Appalachians on top here, as well as these ones here. This is the Muguma boundary over here. And we can confirm, deny, explain some of the constraints that we get from the seismic alone, and then relate these things to magnetic anomalies in the ocean, whatever. There's a lot of things that you can do. This can be unpacked a great deal. Ultimately, this is in the process of being used in a reconstruction where we're going from present day all the way back to the Paleozoic. So this is work being done part-time by my former PhD student, Michael King, and by John Waldron, who's on this call. And so this gives us largely regional constraints that can allow us to test a lot of these models, reconstructing the Appalachians back in time. So ultimately, this work is showing us that we have a new approach to constraining 3D gravity inversions that can work both onshore and offshore over huge areas, especially in areas where the crustal thicknesses change pretty radically and we have really different crustal types. And this allows us to have a varying density gradient. So continental crust can have the density stretched over a greater depth extent, and oceanic can be over a lesser depth extent. And overall, this is showing an excellent correspondence between what we're getting from the inversion and from the seismic refraction, wide angle reflection velocity models, which is nice because they're completely independent from each other. And ultimately, the plan is to put all this stuff into deformable plate models, move them back in time, and hopefully that gives us some insights as to where everything moved in the past. And again, this is work ongoing. Everything looks really cool so far. I think John's pretty psyched about it too. And hopefully we'll have a paper about that in the next 6 months, hopefully. And I am happy to answer any questions if anybody has.
Yeah, John, go ahead.
There's a bit of a mismatch across the Maritime Basin, which of course I was looking at. Do you want to comment on how that arises?
In the Maritime Basin, where? Just here?
Well, I see the wide angle line across the Maritime Basin showing up in yellow dots right across the big green area.
It's super old. I don't really believe it. It's really old. It's from like the late 80s. And I mean,
that's the lithoprobe line, eh?
Those are FGP lines. Like they're very old. I was in high school. And like the methods that we have for modeling this stuff is way better. The distribution of OBSs was not quite so good as they are in other places. I take much greater solace in looking at the more modern lines and seeing how well they match for the most part. I don't lose so much sleep over these guys.
Okay.
Hi, Kim. Phil McCausland here. I've got a question. Thanks for really nifty talk. It's nice to see the progress on this. I'm interested in the deformable plate models. Is there a way yet, do you think, of integrating these different levels of crust into the deformable plate models to try to get depth in them instead of just stretching?
Not yet.
Okay.
Effectively, there is work going on between, so G-Plates is by the Earthbite Group in Sydney, Australia. They've also got a program called Underworld, which they are coupling the two. So you can have numerical models in 3D that you kind of use the G-plate stuff as an input, or you can go back and forth. That's the cutting edge right now, is doing that.
Because that would be analogous to what you have done here by inverting the gravity on it, and then taking, you know, the 2D cuts basically through that. It would be an analogous thing in deformable plate models. Then would be to do the overall deformations, but then to try to put that into different crustal areas basically in the 2D, but then making that a volume instead. That would be a pretty neat.
That's what I make friends with numerical modelers, because they have the clusters to be able to do this stuff. I think that's the next step. I do have debates with them sometimes. There's Sasha Bruna at Potsdam. I was once like, why don't we put this in the model? I want to put this. And he's like, hold up. If you put everything in the model, you're kind of predetermining your answer. And that's maybe not as interesting as letting it be a little bit more simplistic and seeing what the implications are and then doing the mental math.
Yeah, and exploring what the boundaries could be.
Yeah. So I go back and forth on whether I want to prescribe it to death or whether I want more simplistic models to show me basic processes. And then I do the math in my head. That's a philosophical debate that is ongoing. But yes.
If I've got time, I have one other question. And that is about where the transitions happen. That's where all the interesting stuff happens, you know, at the continent ocean boundaries. What do you think is the effective resolution once you go through the process of having done all of this? Because I noticed at one point, maybe it's in this one or in the screech line comparison that you did, where you interpreted, on the lower right hand side, you interpreted, well, you know, possibly the MOHO solution is seeing something that could be intrusions. How much of that might be just a factor of the seismic refraction actually perhaps has got it right, and that the model is basically just fuzzy in that area?
Awesome point. The refraction model is only as good as the OBS spacing, the noise quality, the pick uncertainties, and the modeling approach. And the inversion is a lot more dumb in some ways because it's looking for a smooth model. And so it won't be able to pick up on those kinds of subtleties. I did do some work in Baffin Bay where I did inversions where I forced a MOHO. I used the refraction and said, you got to put the MOHO here and let the inversion tell me what the densities have to be. And that was actually quite interesting because it did show me areas that were anomalously high density. And a lot of them did correlate with areas where we have lots of extrusives. So it's dangerous to do that in a place where you don't have a stupid amount of seismic constraints, because the inversion is then being dictated by your interpolation of your sparse seismic, which could make your life worse.
Yeah.
So it's always a bit of a trade-off. I ultimately found that not pushing the inversion too far actually gave me the most reasonable results.
There's a question in the chat.
I can't see it. Oh, wait, can I? Hold up. I don't think I can do it if I've got a laser pointer on.
The question is from Richard Everett. Does your model extend to the Ottawa-Bonshire structure, or could it be?
Okay. I haven't worried that far back. And if anything, so the original version of this, we'd cut it off. Can people even see my arrow moving up and down?
Yes.
You can see that. Originally we had it over here, but then when we did the Paleozoic reconstruction, we get into trouble because everything slides down to the west and we realized we needed a bigger domain. I haven't actually looked for, there's not a lot of refraction constraints on shore over here. There's lots of earthquake stuff, especially in the States. But I have deliberately kind of averted my gaze from the stuff in the west. I'm sure it's right. It reproduces the observations. But I haven't looked at that in detail because I don't have independent seismic constraints there to give me confidence in what I'm seeing there. So maybe, but it wasn't the focus.
Okay, well, hi again, everyone. So this evening I'm going to continue with the geophysics theme, and as Dana was saying, I'll be presenting interpretations of mainly the Western Superior Province and then stepping back, looking at all the Superior. And these are largely based on the results of new MT data, which combines Earthscope, US Array, and all of the NRCan old lithoprobe data that was inverted by Wu Lin in Wuhan in collaboration with Adam Schultz in Oregon. And I'll also be showing some results of some older seismic tomography. And so I'll be highlighting some of the important roles that these deep crustal and upper mantle structures have played in localizing critical minerals and gold, as well as their implications for tectonic interpretations of the Archean, and touching on whether there is Archean plate tectonics or not. So for those that don't know the geology, the Northern Superior Province in North America, and just here showing the Ontario, Quebec area, comprises two Meso-Archean to Paleo-Archean terrains. And these up here in the north, Riviano, Hudson Bay, they have been defined from isotopic data. And superimposed on these older terrains are Neo-Archean north-south volcanic and metasedimentary belts. And so if we look up here in the domain map of the Northern Superior, what we're now seeing is that all of these domains are trending at a high angle to those that are in the Southern Superior Province. If we step back again and look at the big picture, and now looking at some seismic tomography, what we can see is that the Hudson Bay and the Riviera Arno terrains comprise the Northern Superior Protocraton. And so we can see in this west-looking view of a 3D seismic tomographic image that here, that this Northern Superior Protocraton has got the part of the Superior with this deep lithospheric keel going down to about 240 kilometers. And so that differs now a lot from the Southern Superior Province. And this is comprised mainly of Neo-Archean sequences with local Meso-Archean remnants and some other xenolith examples of Meso-Archean being present at depth. And so the sub-province boundaries, as we can see through in the southern part, in contrast to the north, generally trend east-west, and that's also reflected in this geological map of faults mapped at the surface. And so a notable exception of that is this Kappas casing structural zone, the KSZ on that image, which trends northeast-southwest, that I'll get back to. So again, looking at other tomographic data, this time P-wave tomographic data, this is a 150-kilometer depth slice for the Western Superior, and this is showing a major contrast from east to west. Within the west, a high velocity zone shown by the warm colors, and in the east, dominantly lower velocity areas. They are defined in more the cooler colors, just with some remnants of high velocity material scattered within it. So the contact between these two different domains is trending north-south up in the northern part here, just here at the latitude of James Bay, and then trending as we're getting towards Lake Superior area, more northwest, southeast. And so this orientation of these deep structures here in the upper mantle of 150 kilometers there is totally oblique to those that are mapped at the surface. And these here, the sub-province boundaries, which were going east-west. And we can see that that contact is continuing under all of these different sub-provinces. And so one thing that's important in looking at that image is that we don't see any evidence for east-west accreted terrain boundaries that have been interpreted in the standard plate tectonic models. And we see the same general trends as in that deeper slice here, now just in the uppermost upper mantle here at 50 kilometers in depth, where again, all the contacts between the high velocity area in the west and the low velocity in the east, they are at a high angle to the sub-province boundaries. And there are just a few local trends of some blocks which may be significant or not when they start to parallel some of these boundaries. So if we look here now at a zoom in on the area of this contact zone, what we can see is that there are both Archean and Proterozoic massive sulfide and some other magmatic sulfide deposits shown here in the legend, with the Archean ones being with the stars and the Paleoproterozoic deposits here in the smaller symbols. And there's also a carbonatite here, which contains uranium, niobium, and rare earth element mineralization. And these are sitting on the margins to these high velocity domains. And if we plot here schematically these concentric structures that I've observed in the lower crustal component from an aeromagnetic image that's been enhanced to show such features, we can see these concentric structures here that are fitting in between these two fragments of the high velocity material within overall this low velocity zone. And so these concentric structures, in comparison with these numerical models here by Barov and Gauya, I'm interpreting as being due to mantle upwellings as exactly what we're seeing here, and these were along the Superior Province. And it's interesting that in these models, when a regional stress field is imposed in that numerical model, we see these linear extensional structures, whether they're tensile fractures, normal faults, and these parallel the imposed maximum compression direction. And so there are also, in addition to the concentric structures here in the northern part of the James Bay area, where we find the Eagle's Nest and Limestone House mineralization, these north-south trending structures. So very poor resolution in this long wavelength component, but they are present. And I'll be showing in this talk that these structures further south show up very well in this higher resolution MT data. So looking at a view now of a model in 3D of isosurfaces from the seismic tomography. When you first look at this, it seems to be a real mess. And so in Australia, we say that it's looking like a dog's breakfast. You know, it's just really trying to interpret this image model just appears at first glance as being really hard. But when we start to outline discontinuities between domains, especially these high and low velocity domains, I've come up with this interpretation that is appearing as a rift transfer fault model. And so what we can see is that an interpreted terrain boundary between these totally different western and eastern terrains in terms of their velocity structure appears to have been reactivated as a transfer fault, in fact, a transfer fault zone during rifting associated with this more north-northwest, east-southeast, the south-southeast extension. And so these alternating zones of highs and lows in that vertical view looking down at the isosurfaces, they're interpreted as a series of Horsten grabens. And so not only do the velocity values differ between the east and the west, that the form of these isosurfaces differ between the east and low velocity zone as shown here. And so this is a view looking obliquely at this northeastern part of the model at the low velocity zone. And what we can see is that here we've got more domal structures, that these isosurfaces are closing vertically. And it's tempting to draw the comparison here with the interpretations of Jean Bédard for the Archean that are showing these diaperic TTGs, which are rising vertically. In comparison, in the western high velocity zone, these isosurfaces close downwards and resemble mantle drips in these models. So looking at this other data set now, this is the magnetic magnetotelluric data. And these show in this image, first of all, of the upper crust here at the mid crust at 23 kilometers, that we've got quite a mix of orientations, both paralleling in the northern part here, some of these sub-province boundaries, and in other areas, we can see more north-south zones. And so these colors from the resistivity model are superimposed on the enhanced deep crustal source aeromagnetic image. And so where we see some of these more north-south features coming out in the MT data, we're also seeing those in the lower crust from this enhanced aeromagnetic data. When we look deeper at this image now in the upper mantle here at 72 kilometers, we can see that there are second depth slice shows these alternating zones of high and low resistivity shown by these different color bands, which are clearly trending north-south through here, north of the Quetico, or either the northern or the southern margin. It seems to change slightly eastward, as well as some northwest-southeast trends. And looking now at a vertical view again of 3D conductive MT isosurfaces in this time, we can clearly see that up in the northern part up of the study area covered by the MT data, these MT high conductivity isosurfaces trend north-south. And we can see just extending from these north-south features, series of fingers which are rising obliquely eastwards and westwards into the upper crust. And so looking in 3D, we can see that much clearer, where with this model, we see the mantle zone is very broad and north-south here, but at the moho and further in the crust, these fingers are rising up obliquely. So zooming in at Red Lake, we can see the gold deposits here in yellow, and the smaller ones just showings. They are on the margins of just where we see the fingers penetrating up through into the crust. And the Great Bear deposit that's subject to the next talk is just in a mirror image here on this other margin. So when I superimpose a gravity image now taken from satellite gravity data for the uppermost mantle and put that in the 3D model at 40 kilometers, we see these irregular domains in the upper mantle are also important in localizing not only where these MT fingers penetrate, but also the mineralization is on their margins. Here's one of these other fingers coming through. In the southeast of the area, and this area is covered by even higher resolution MT data that results from the US mobile array, we're seeing both some of these finger-shaped anomalies rising up, but this time rising up trending northwest-southeast, with Hemlo overlying one of these anomalies, and also just zooming in on this area through here in an oblique view, these mushroom-shaped features. And so it's interesting when one puts this contact that I was showing before from the seismic tomographic data, the contact between the low and high velocity zones, we see that the major gold deposits also occur in the vicinity of that zone, and this finger is rising up parallel to that contact that was determined using another data set. And so looking at the big picture, what we're seeing is that the conventional interpretation of applying a modern plate tectonic model to the Superior Province is not supported by the geophysics, that we don't see any lithospheric scale terrain boundaries that are trending east-west at all. And the contacts between these zones of different velocities, a trend going right beneath all of the Western Superior, which is inconsistent with these accretions of east-west arcs and back arc basins. And so again, looking at the big picture and putting the contact between the high and low velocity zones through here, we see that the general trend of that contact, even though it's subsequently undergone rifting, is sub-parallel to the contact between the Riviera Arno and the Hudson Bay terrain based on isotopic data. And if we plot some deep gravity structures, and here we can see that these features also seem to fit in with the same sort of rift model that was applied in the Western Superior, where the Kappas casing structural zone may have indeed been formed in the Archean as another one of these rift-like structures. And so would this major feature which I haven't got time to talk about today, that goes right across the eastern part of the Superior. And it is offset by a structure that's also parallel to the Waswanipi-Saguenay corridor. And that Waswanipi-Saguenay corridor is controlled a lot of mineralization right from the Archean through to the Proterozoic. And when we superimposed this image from David Mole, the isotope data developed in metal earth, even though we need a lot more data, we can see that the trends in the hafnium lutetium data parallel, again, these trends, these terrain boundaries. So basically, looking at a little bit further than covered by the detailed MT data, we see that these transverse structures that such as go through Red Lake intersect in these concentric features that I showed before in the model. And when we plot the location of the boundary here to the Northern Superior Province, these upwellings are on that margin. And again, we can see in that model that these north-south structures also really agree with that model, given that they now intersect in the concentric zone. So I've shown you now evidence then for two different generations of transverse structures, and combined that they are not interpretable in terms of the conventional plate tectonic models. So thank you. So are there any questions?
That was great. Thanks, Lyal. Yeah, if anyone has any questions for Lyal. Yes, Felix.
So Lyal, what are those fingers? And why is there mineralization above them?
That, Felix, is the big debate, that the first sort of fingers, and that term of a finger comes from the fingers of God that were recognized in South Australia from similar MT data, which rise up beneath the Olympic Dam IOCG deposit and also several other IOCG deposits. And there, those fingers rose up similarly between these more refractory upper mantle, and that's what we seem to be seeing in the Western Superior, where we haven't got such good data, but the satellite gravity is suggesting that these more elliptical and irregular features could also be equivalent of the areas where we've lost upper mantle through mantle dripping, similar to at Olympic Dam. So there have been various models. People invoke graphite from the mantle traveling up. There are also others that say in some areas that it could actually be some magma, but that's difficult to explain. And also there are other models, some of which I'm afraid I can't talk about just here today, as it's ongoing research by others. But in some areas that they think that maybe there is a difference between what the source in the mantle and in the crust, and that we could be having sulfides being carried through by hydrothermal and carbonic fluids in the crust. But no, that's the big question. So you've picked the topic of discussion at the moment.
Fried, did you have a question? And then Kim.
Yeah, I wonder if you are aware of studies in northwestern Ontario where the striping, east-west striping is so prominent that the Proterozoic deformation has affected structures like the Quetico fault zone in a big way. It's done by American colleagues, I think, in Minnesota or somewhere in the Middle West. Are you aware of these studies?
Oh, yes, and there are also more recent results in Chris Yakamchuk's group as well. But what we're seeing here, and indeed there have been other interpretations of these north-south structures coming out of the Metal Earth Project and by Natural Resource Canada geologists, and they were suggesting a Proterozoic age. But I think this correlation between mineralization that we're seeing and the controls on the MT data and really are showing that they're Archean. Otherwise, you wouldn't expect to be seeing such a relationship to known Archean intrusions, as well as intrusions of mafic, ultramafic rocks and carbonatites, which are much younger. So
second question, if I may. The egg carton structure you had in much of the area, and of course, diapuric rise and intermediate sinking of heavier stuff. Have you got a correlation with the composition of the rocks there? Or the composition of the material that makes these egg carton structures?
No, I mean, here we're looking in the upper mantle. And so, you know, it's really just pointing out, you know, a rather tenuous comparison. But it's interesting to see that there are differences in what was interpreted by the people who did the seismic tomography in the West. These higher velocity area, they interpreted as being older rocks equivalent to the Northern Superior province, just based on the seismic velocities. But no, we don't have enough spread of either isotopic data, and especially we don't have a good enough database of xenoliths to be able to tell it. But no, you've raised a good point, and there's certainly a lot more needed, but especially to continue the excellent isotopic work that's being done in the Metal Earth project.
Okay.
And then we can do one more quick question from Kim.
I just have a quick question about, is there any way that any of these patterns are the acquisition footprint?
Oh, no.
Okay.
And that's exactly what you were saying there is the first thing that I was looking at. I don't believe anything I see just in one data set. And that's why I was superimposing the long wavelength component of the aeromagnetic data, which was a deep crustal source, with what I was seeing in other data sets. And the fact that they both agree really tells me that those features are real. If I'd only seen it in one data set, you know, then it can be debated. And then when I haven't had time to show the gravity data, but we also see the same features precisely in the gravity data for the long wavelength and crustal components. In addition, we see these strange holes and rifts in the upper mantle. And so all combined, even though we don't completely understand what's happening, it certainly can't be explained by the standard tectonic models.
Okay, great. Okay. So hi, my name is Maggie Laverge. I'll be talking about the structural controls on gold mineralization on the Great Bear property, but more accurately, because that is the topic of my master's, and I only recently started my master's. We're about 2 months in. I'll be talking mostly about the structural evolution of the LP fault, which is the gold-bearing fault, or the control on mineralization that we're seeing along the Great Bear property. So without further ado, we will start with a regional geology and going over the general context. Luckily, the broader scale was already gone over by Lyal just now. We'll be looking a lot more specific than getting into the project-specific geology. And after we have our context, we'll go over the structures that we're seeing along the LP faults and making the case for dextral transpression, and ending with the conclusion and the questions that still remain. So the Great Bear property is within the Uchi subprovince along the margin with the North Caribou Four. The Great Bear property is a brand new world-class structurally controlled gold deposit with a 5 million ounce resource estimate that was put out just last year. It was only discovered 5 years before that, so it was pretty exciting. And it's located about 25 kilometers south of Red Lake, Ontario itself. It's just south of the productive Red Lake Gold Camp, which you'll see up here. So the Campbell Red Lake Mine, the Coutts mines, and all of them within the Red Lake Mine Trend. It's just about 25 kilometers south of there. And mineralization within the Red Lake Mine Camp is typically associated with these mafic foliatic Meso-Archean Balmer assemblage rocks, to a lesser degree with the Balmer and Slate Bay assemblages, but typically within the Meso-Archean. Now on the Great Bear property, what we're seeing is these felsic calc-alkaline Neo-Archean Confederation assemblage, and then what was mapped by Sanborn Berry in 2004 as unknown supercrustal assemblage, but it was also considered to be Neo-Archean. So some additional work is being done at Laurentian right now on dating and reclassifying these assemblages. So we will probably get some better constraints on that soon. So in terms of regional deformation, we already had some discussion about this, but what we see on specifically on the Great Bear property and within the Red Lake Greenstone belt is associated with these east-southeast D2 structures that are considered to be a result of the Oceanic orogeny. And they result in this Red Lake mine trend, which connects the major producing mines from Coutts and Campbell Red Lake gold mines. So that's up in this area. So if Balmertown's here, Coutts is just up here. And so these are southeast trending structures. And as we'll see on the Great Bear property, we have the LP fault, which is a northwest to southeast trending structure as well. So yeah, getting into deep diving into the project itself. So on the project, we have the major northwest southeast trending LP fault, which was named such after the 2006 Zhang and Calvert lithoprobe study, which is what defined the fault in the first place. In the southern portion, we have the mafic domain, which was the unknown supercrustal assemblage. So that's our green schist facies, mafic volcanics with beds of argillite and iron formation. But then up to the north is where we see the felsic domain. And that's where we're seeing our green schist to amphibolites facies, metasedimentary rocks, metavolcanics, and our subvolcanic porphyries. And it's within this felsic domain that we have the LP fault zone, which is where we're seeing our mineralization. So for my first summer field work, what we did was we spent time doing both detailed and regional mapping. We did some detailed mapping all along the LP fault zone. So starting up with one deposit up here in the northern portion, with more outcrop in the southeastern portion. It should be noted that there is, if anyone has worked in northwestern Ontario, there is limited outcrop simply because of the topography. And so outcrop is not necessarily where the mineralization is, but where there is outcrop. So we also did some regional mapping of other areas, but we were a little hampered by the amount of outcrop that was there. So getting into where the mineralization that we're seeing is, though, we have 3 styles of mineralization, all associated with different zones. Within the main area, the LP fault zone, it's actually 6 contiguous shoots of gold mineralization, and it's foliation controlled disseminated gold, as well as vein hosted gold. So it's foliation parallel and oblique quartz veins. So that is this entire area in here. Then within the mafic domain, we have this regional fold. And this is where we see sulfide silica replacement within the limb zone. So that's exhalative pyrrhotite and silica flooding with gold associated in there. And then finally in the hinge zone, we're seeing these quartz veins that are axioplanar to the fold itself, which also holds significant. Volumetrically, the majority of the gold is within the LP fault zone. So now that we have that out of the way, let's get into the actual structures. There's 2 interpretations for the structures that we're seeing along the LP fault. One is that we have early thrusting along our main foliation plane, followed by a later dextral transcurrent faulting, or that we have a single long-lived dextral transgression event. I'll be making the case for a single long-lived dextral transgression event. And so to go over that, let's first look at the structures themselves, which can be broken up into early generation structures and later generation structures. Our early generation structures consist of this steeply dipping penetrative foliation, moderate to steeply plunging isoclinal folds, as well as mineral stretching lineations. So our main foliation plane, it's penetrative, it's northwest southeast striking parallel to the LP fault and steeply dipping. It is parallel to bedding and locally transposes bedding. So getting into that, we see these, so axial plane, yes, our foliation is axioplanar to these folds that we see that are tight to isoclinal and often transpose any previous bedding or quartz veins that we see. There's two populations of our foliation or our fold axes. One is steeply plunging and roughly north trending, and this is what we're seeing across the property. But specifically within the southeastern portion of the LP fault zone, we're seeing these shallow to moderately plunging southeast trending fold axes, which are associated with these isoclinal folds. So keeping that in mind, as we get into our mineral stretching lineations, we're seeing this same behavior where we have steeply plunging north trending lineations across the property, as well as another population of these shallow to moderately plunging southeast trending lineations. But in both places, they seem to be defined by these elongated feldspars, of course, phenocrysts and porphyries, and these aligned micas and metasediments, and they're coeval. It seems to be a rotation of lineation, and I'll talk more about that later. Overprinting this, we have a second generation of structures, and these consist of these Z-shaped isoclinal folds here. So these are our tight to locally isoclinal Z-shaped folds indicating dextral movement that are east-west striking, and they range anywhere from moderate to steeply plunging. Locally associated with this, we see a steeply dipping axial planar crenulation cleavage that seems to be preserved best within our mafic domain. Now, additionally, we see shear bands, which consistently indicate dextral shear, overprinting our main foliation plane. And additionally, we see the boudinage and dextrally back-rotated intermediate to mafic dikes. This one was specifically in the southeastern portion of the property where we see them most. So getting into the evidence for and against two discrete events, primarily on across the property, we're really seeing a lack of shear sense on the vertical surfaces, but significant shear sense on the horizontal surface. And so even though we have a little bit of a bias and that we don't see as many vertical surfaces as horizontal, we're not seeing any asymmetry. And we did get several thin sections back recently where we'll be confirming this as well. But if we don't have any significant shear sense on the vertical surfaces, this indicates that we can't have significant vertical displacement. And additionally, the metamorphic grade across the LP fault is consistent. So we have a gradual change from greenschist to amphibolites facies metamorphism from the mafic to the felsic domains, but there isn't a sharp change indicating that we had two distinct metamorphic events associated with two distinct tectonic events. So now let's get into the positive evidence for dextral transgression. So we have a main foliation plane, which you can see very nicely here within our porphyritic rock. And then we have the development of a coeval oblique foliation, which forms specifically within these more competent years or within our mafic dikes. And these dikes are parallel to the surrounding rock, indicating that we have some degree of shear forming this oblique foliation. Now, this is the same photo, but at a different angle. We're seeing that same main foliation, and we're seeing this anti-clockwise oblique foliation. And along both of these foliation planes, we're seeing these steeply plunging stretching lineations. I know it's a little bit difficult to see it in this photo, but we have the elongation of our feldspar phenos within this area, indicating that we have at least some degree of vertical extension at the same time that we are having this, this shearing. Now, additionally, we're seeing dextral rotation of strained porphyroclasts within that porphyritic unit. So we can see the S fabric defined by the orientation of the phenocryst, as well as the rotation of the strain shadows into the C plane. You can see it a little bit better here. So we know that we have some degree of dextral movement. Now, where we're seeing this dextral movement, I took this photo top down, and then next to it, we had a vertical surface, and we're able to see that we have vertical stretching of these phenocrysts, which are dextrally rotated here. We're seeing that same vertical extension, indicating that we have to have some degree of transpression. Now, additionally, looking at our fold axes. So in both our F2 and our F3 folds, this was taken in the southeastern portion of the property, where we have these F2 folds that are very isoclinal. We're seeing the fold axes are rotated into the lineation. So where we had our moderate shallowly plunging lineation, this is the orientation of our fold axes. And then over in, this was in a more mafic area where we're seeing our dextral or our Z-shaped F3 folds. It's sort of difficult to see, but we have the fold axis. The fold axis is rotated here into the plane of into the lineation, which we see the lineation on other surfaces in that same area to be in the same orientation. So now finally we get into the lineations, which I mentioned earlier are steeply plunging in certain areas and moderate to shallowly plunging in other areas. So we believe that they're being rotated towards the horizontal plane. And the difference between the plunge and the stretching lineations could be due to three possibilities. One is that we have a difference in the finite strain undergone in the southeast portion relative to the rest of the LP faults. Another is that we have a difference in the simple shear to pure shear ratio along the LP faults, or that we have a difference in the obliquity of the shear direction and the pure shear strain axes. For the first option, we would need to have a gradual rotation in the orientation of our lineations, and we're not seeing that. We're seeing those two distinct populations of a steeply plunging and a moderate to shallowly plunging lineation, which would indicate that we either have that difference in simple shear to pure shear, or that we have an obliquity between the shear direction and the pure shear strain axes, which would indicate triclinic transpression as opposed to monoclinic. So finally, talking a little bit about the gold mineralization, we believe that it was likely in place during this major regional dextral transpression event, this same event, which resulted in the formation of the structures that are controlling the orientation and the geometry of the gold-bearing zones. So preliminary conclusions is that the LP fault is a dextral transpression zone. So we have a lot of questions that we still need to answer, obviously. Is the LP fault an expression of the regional deformation and the foliation forming D2 event that we see across that red lake greenstone belt? Are we seeing just that same red lake mine trend? Or is this a discrete later dextral transpression event that is unrelated to D2? And finally, what are the structural controls on gold mineralization? Is the LP fault concentrating it, or are we seeing, essentially we want to get into, without too much bias, what exactly is controlling the gold mineralization? So finally, thank you so much for your time. I know it's been a very long night of talk, so thank you for sticking around, and thank you to Bruno for his patience with me, and to everybody at Merck and Kinross for all of it.
That was great. Thanks, Maggie. Does anyone have any questions? Yes, Reed.
I have a question about a train of folds, small scale folds, that it was a slide just before the synoptic lineation diagram.
I'll bring it back up, one sec. So it was, was it this one, or did you want to go back to?
No, it was a train of asymmetrical folds, about centimeter scale to decimeter scale.
This one, no. This one.
It was before that, I believe. Yeah,
this one?
No, you overshot. Go back. The lower right figure here. Oop. You're going too fast for my brain.
Sorry. I will go slower. I believe if it's the lower right figure, then mention is this one.
Okay, this is the one. The lower right hand figure. Okay, with the brownish scale card. Could this be a former cross-cutting vein that has been folded in this asymmetrical form while the main rock has been flattened vertically?
It's definitely possible. The original orientation of the vein was likely oblique relative to the orientation of our, because this is within a metasediment. So it was likely oblique to the metasediment itself. Sorry, my dog is getting very excited right now. It's about time to go out. So we could have some degree of flattening associated with it. But right now we believe that there's a certain amount of extension actually associated with it. So this will be something that I'll definitely be talking about with Bruno tomorrow.
A second comment. It looked to me, looking at your rocks, that you have a lot of asymmetrical boudinage on the meter scale or less or smaller. So that creates some of the obliquity that you have, and you measure the directions. Don't know which. Yeah, this is the right lower figure there. Is an asymmetrical boudinage structure, and you can see the boudins here, and there's a slip plane running from the left upper corner to the right lower corner. So the way I diagnose this would be boudinage. You can see down there, geometry is just very perfect for boudinage here. So I would say lateral stretching here of the rocks and causing some of the obliquities in the foliation and in also other structures.
So luckily we were able to measure. Sorry, so I was going to say we were able to luckily measure the orientation, and so up here what we're seeing is the orientation of the plane of the boudinage and the shear bands that we saw throughout, which was quite interesting because it was consistent with the orientation of our F3 folds. Of the planes of the F3 folds.
I like your main conclusion anyway.
Oh, good. I'm glad.
Does anyone else have any other questions? Lyle's just put into the chat that you can see these dextral shear bands and boudins are also apparent in aeromag data.
Maybe I can make just a general comment. It's just something I read in the Globe and Mail, and it was quite interesting. This was a discussion that we should leave all the gold underground. We do more damage to our environment. They're trying to dig up this gold, which is really just in minute little, more and more. We are mining just minute bits of gold while we can just recycle it. I know it's very interesting structurally to try to make the argument that these little things get just concentrated in certain areas. And I've done gold exploration, and you can see it in the outcrop, and you have to send it in to get it assayed, and then you get some answers back. But anyway, and it's just interesting that it was in the Globe and Mail. So there's lots of other interesting things for structural geologists to study besides trying to look for gold. But anyway, it's more a Western opinion, and it will not be shared by Eastern Canadians, I think. But anyway.
If I could just comment on that whilst the main product to a lot of these mines in the Superior is gold, there are also a lot of secondary minerals which everyone is now seeking for the energy transition. And so as a byproduct of all the exploration for gold, we're also opening up areas that are going to be producing some of these other minerals, which we don't normally talk about in conjunction with the gold, but they exist.